Quadratic factors are not as exciting as you're probably hoping. It's boring. It's the same thing. Okay, there's really not that much new. So again, if you have repeated quadratic formula factors, something's going to happen. If you have distinct, let's just quickly go through these. Distinct quadratic factors, let's say a1x squared plus b1x plus c1, all the way up to a sub nx squared plus b sub nx plus c sub n. And again, these have to be prime, right? Because if these factor into linear factors, then factor them, make them linear. But if these are prime quadratic factors, then what we get is p of x over q of x is now, instead of some constant on top, it's going to be a linear function on top divided by that first quadratic factor. And then again, I'm not going to write it that many times. They're all going to have linear terms on top. Okay. But it's really not much worse. And if they were repeated, what do you think would happen? If they were repeated quadratic factors, well, again, I'll just write it down real quick. I'm not going to do it fully, but it's basically the same idea, right? You'll just have a linear factor on top divided by that quadratic factor that's repeated. And then you have n of them, where every time, just like with repeated linear factors, every time you just add an exponent. So it's still that, oh, whoa, right? You have n of them now. Just like we had with linear factors, it's just combining what we did with linears with what we know about quadratics. Okay. The only real difference for quadratic stuff, again, factor the quadratic if you can. The only real difference is that you get a linear term in the top. So you get some extra coefficients you got to look for. So in this one, I don't want to focus more on the calculus. The calculus is pretty straightforward. And I don't even really want to focus that much on system of equations. If you want more practice with systems of equations, that's not calculus. And I can give them to you. It's important and I can give it to you. But I don't want to do it in these videos right now. So we're just going to get practice setting them up. I will do full problems in the selected homeworks video, but right now I'm just trying to teach this topic. Okay. So example 5 is going to be set up. I just want to show you some setups. Set up the partial fraction decomposition for the following fractions. First one is just going to be 2x minus 3 over x cubed plus x. And again, we can't just divide it out because the factor on top is not at least as big as the degree on top is not at least as big as the degree on the bottom. We need a factor. We need to factor that denominator. We get x squared plus 1. We have one linear term and one irreducible quadratic. I guess you could factor this if you wanted imaginary numbers, but no, an irreducible quadratic. So to set this up for partial fractions, it'll be some constant divided by the linear function plus some linear function, let's use different letters, divided by the irreducible quadratic. And then you just multiply both sides of the equation by the LCD and solve for a, b, and c using either the equating coefficients method or the strategic substitutions method. And again, I had to check. I don't remember what I called them. And again, in this one, strategic substitution is not going to work out fully unless you plug in like x equals I or something. We're not really dealing with complex valued functions. Actually, I'm curious whether that would work. I think it might, but complex numbers would add another dimension. And so don't take my word for it. I should think about that though after this video. Okay, so that's how you'd set it up. System of equations. We'll do more of those in the next video, but just trying to show up the different setups, combining all of these topics. B, let's do B on the next page because it's got a little going on. 1 over x squared times x squared plus 3x plus 5 squared. Careful. Is this an irreducible quadratic? Or is this a repeated linear term? It can be factored. It's not an irreducible quadratic. If you use the ax plus b formula, treat this first guy as an irreducible quadratic, you're going to have to do partial fractions twice, I think. At any rate, whatever happens is going to be messy. This is a repeated linear term. Please watch out for that. Whereas this is a quadratic that cannot be factored. What multiplies to 5 that adds to 3? No rational numbers. Okay, so this is going to be some constant times x, or divided by x, plus some other constant divided by x squared, repeated linear factors. And then we have a repeated quadratic factor. So that'll be cx plus d over x squared plus 3x plus 5, plus another linear factor divided by that quadratic factor squared. Repeated linear factor means do it twice, or 3 times if it were x cubed. Repeated quadratic factor means do it twice, or 3 times if it were cubed. Whenever you have a linear term, it's just a constant on top. Whenever you have a quadratic term, it's a linear term on top. And again, don't be fooled. This is a linear term with multiplicity 2. This is a quadratic term with multiplicity 2. So even though this looks like a quadratic, think of it as a linear term with multiplicity 2. Okay? This would be a heck of a lot of fun to do all out. System of equations with 6 unknowns. Woohoo! All right. Part C. X squared plus 5 over x times x plus 1. Don't forget to divide if you can. Long division is going to make things easier for us here. So this is x squared plus 5 over x squared plus x. Now we divide it out. The degree on the top is at least as big as the degree on the bottom. We can use long division here. What happens when I have x squared plus 5 and I'm dividing it by x squared plus x? Well, what do I need to multiply this by? Sorry, what do I need to multiply this by to get something that cancels with the x squared? Just 1. That'll leave us with x squared plus x when we multiply it out. And we subtract. The x squareds will cancel. We're left with negative x. Oh, I forgot. It's good practice to write this as x squared plus 0x plus 5. I don't do a lot of long division anymore. Now 0x minus x is negative x, and then bring down the 5. That's our remainder. So this is 1 plus our remainder, which is 1 over x squared plus x. I'm going to go back and write x squared plus x like this. And now, wait. What did I do? Oh, yeah, no, there's no problem. So we can't integrate this yet. Now we have to use partial fraction decomposition on this new guy. So this is going to equal 1 plus whatever this new guy is. For a second, I thought I already did partial fractions, but we didn't. So it'll be 1 plus, that's a over x plus b over x plus 1. We'll have to go off and do this. Okay, but again, we're just setting it up here. So this is the final answer to what I'm having you do. Hey, where did you, whoa, what just happened? Did I hit the erase button and now I switched? I didn't think I hit the erase button. I've done this before. This is the final answer. Now, if you were curious about where to go from here, what was it? It was something like this. You wouldn't worry about the 1. The 1 would just stick around for a while. But when you're actually solving it, you would say, okay, so 1 over x times x plus 1 equals a over x plus b over x plus 1, like so, and then you'd multiply both sides of this equation like so. And then once you had an answer, you just replace the b and the c in here, and you'd integrate all of this. All right, again, this is just some practice showing you how to use all of this stuff together, when to divide, when you have repeated linear terms, repeated quadratics, non-repeated linears, non-repeated quadratics, putting it all together. And then you have to solve those systems of equations, and then you have to integrate. We'll put it all together in the selected homeworks problems video, but these are all the concepts. Let me know if you have any questions, and good luck.